Welcome back, everyone, and to our second talk of the day at the LCA kernel miniconf. Next up, we've got Paul McKenney, who has been a programmer for a very long time and has been working on parallel hardware for approximately my entire life. He's a software engineer at Facebook, where he works as the maintainer of the RCU, or read copy update implementation of synchronization primitive within the Linux kernel. And today he'll be talking to us about the rcutorture test suite. Paul has asked if he'll be taking questions during the talk, so if you want to get your questions in via the questions tab in Venulus as he's going along, we'll do our best to get them to Paul during the course of the talk, and there'll be a Q&A section at the end as well. Please welcome Paul.
Thank you, Andrew. So why would anyone want to torture RCU, I suppose, is a starting question. And let's face it, synchronization primitives can be somewhat obnoxious to use. RCU is a synchronization primitive. When you're using them, sometimes it feels like they're torturing you, so why not get back? But before we start torturing RCU, I would like to call for a round of appreciation for these projects and the people behind them. These guys don't always get the respect and appreciation they deserve, but their efforts are really important to making all our software work as robustly and reliably as it does. So big thanks to them. Okay, so some of you are probably thinking, hey, Paul, shut up and let me start torturing. Before we get to that point, though, the URL at the bottom is an overview of a bunch of blog posts covering this material, and there'll be URLs at the bottom of some of the slides that will have more information on the topic in that slide. For the people who want me to shut up so they can start torturing, I'm sorry, but I'm not going to shut up immediately, maybe never. But if you want to start torturing, this slide is for you, all right? If you have a system that can run QEMU and KVM, and any modern x86 system will do just fine, and there's a bunch of other ones as well, you set your path up as shown there. And if you have a lot of time, all you have to do is just type kvm.sh, enter. What that's going to do is it's going to torture RCU with 19 different scenarios. How that's going to work is it's going to build a kernel for one of the scenarios. It'll then do a 30-minute run by creating a guest OS and then running rcutorture within that guest OS. When it gets done with that, it'll build the next kernel and so on through all 19 scenarios. As a result, this is going to take like 10 or maybe even 11 hours, depending on how quickly your system builds kernels. If you have a system with a lot of CPUs, this is a really wasteful process because a lot of those scenarios use only 1 or 2 or 4 CPUs. So if you have 64 CPUs, the next line is more appropriate, kvm.sh-cpus 64. And what that's going to do is going to run the scenarios in 2 batches. So it's going to build a whole pile of kernels one at a time, build them, and then when it's got them all built, it's going to create a guest OS for each of the kernels it just built and run them concurrently for 30 minutes. When it gets done with that, it'll build the rest of the kernels one at a time, and then it'll run all of the kernels produced as guest OSs again. Then it'll summarize the results. So that allows you to get done a lot faster. That's going to be, well, I don't know, maybe 1-2 hours, depending on how fast, again, your kernels are built on your system. But if you're running different systems, keeping track of which CPU has which system has so many CPUs, for that matter, can be a little obnoxious. So you can just say kvm.sh all CPUs. And that'll just look and see how many CPUs are there and use all of them, which makes everybody happy. Well, aside from anybody who might be trying to use that system for something else, but you can't have everything. And you can also tell it how long to run. So -- duration 1D says 1 day, 24 hours. What this will do then is that if you have 64 CPUs, it'll act just as it did before, but it'll take 2 days, kind of a weekend run, to run through all of the scenarios. If you have 128 CPUs or more, you can run all the scenarios in one batch, build all the kernels, run everything in parallel, be happy. In this case, we're setting the duration to 12 hours. One important safety tip, you've got your kernel source tree you're doing this in. If it has things like tags files or cscopes databases, you'll want this trust make thing. That's going to do 2 things for you. Well, one, it's not going to do a make Mr. Proper or make disk clean at the beginning of the build, each build. And and that means that you'll be able to reuse build products. Of course, there's some risk in there. You may have a problem that's caused by an earlier build. But the nice thing about Trust Make is that it's not going to destroy all of your tags files or cscopes databases. If you just want to torture one aspect of RCU, for example, I modified SRCU some last week, so I'd want to torture SRCU, and this is one way to do it on the next line. Given 28 CPUs, if I say -- configs and then list all of the SRCU scenarios, there are 4 of them there, I can also put 2* in front of it to say run each of them twice. So what's going to happen with this thing is it's going to do 4 kernel builds, and then it's going to run 8 guest OSs, 2 for each kernel, and do that by default. We haven't said, so do it for 30 minutes. If you have a boot bug that happens rarely, it's going to be really annoying waiting for the kernel build each time. And so KVM again allows you to reuse the build products from a previous run. So if you just run kvm.sh like the previous 5 lines, in this output there'll be a results directory and a big path name. You take that path name and drop it in as a second argument to kvm.sh. And in this case, we can set the duration of the runs to 45 seconds, 45s for 45 seconds, and that allows us to do a huge number of boots really quickly, and hopefully be able to reproduce the bug we are chasing. If you have a large number of systems, then KVM Remote is for you. You can give it a list of systems, the names as you'd use to SSH into them, and you'll usually need to give it configs. The CPU's 80, each system has at least 80 CPUs. Configs, you want to usually run a lot of them. CFList is a keyword that says all of the 19 normal scenarios. So we're going to run 19 times 15 scenarios plus tree 10. So it's going to do a lot of torturing in a short period of time. That's something I normally do something like that for my testing. Okay, so that's how we start testing. So one question is, what's success look like? And if we just run the stock thing without specifying configurations, we get those 19 scenarios. And the important thing is that all of these scripts, all 3 of them, will give you an exit code of 0 if there were no problems detected by the test. And this can be really useful. You can take any of those scripts and hand it to git bisect run, for example. And yes, I really have done git bisect run with KVM Remote. It helps you reproduce and test things involving difficult to reproduce bugs much more readily. Okay, there are other kvm.sh parameters. I'm not going to go through these in violent detail. kconfig allows you to specify kconfig arguments. You can specify kernel boot arguments as well. You can tell it to run either KASAN or KCSAN. You don't get to run both of them at the same time. Both of these guys generate big binaries, big VM Linux files, so be a little careful of your disk space. And KCSAN requires recent compilers. Clang 11 works for me, but you'll need to check for you. You can torture different things. If you're not upset enough at RCU, you can torture locks, for example. If you're running a special purpose thing, if you have a lot of CPUs, you can do -- dry runs scenario and tell it to list the scenarios. And what that'll do is won't actually run the tests, but it'll tell you what the batches are going to be. In other words, what scenarios are run in what order, and that can allow you to choose the -- configs or the -- CPUs argument appropriate for whatever you're trying to test. All right, maybe you can't decide what you want to torture. Well, there's the torture.sh script, and it tortures a little of everything. I use it as kind of an acceptance test before I do a pull request occasionally. I also use it for -next testing. Now, this does take some time, like about 11 hours on a heavy-duty laptop. It does not run KCSAN by default. If you do that, you're looking at 14. It's got a lot of arguments and controls torturing, but we'll leave those off due to time. Maybe you want to run a debugger. Well, --gdb does that for you. You only get to run one scenario at a time. Sorry, I didn't want to mess with having multiple parallel debugging sessions. And well, if you want to do that, send me a patch, okay? One safety tip: you don't get to use the gdb break command. And the reason is the Linux kernel really doesn't like gdb rewriting as binary. So use hbreak, which uses the hardware breakpoint registers. Use that instead, and life will be a lot better. You also have to be fast once you hit a breakpoint. Otherwise, all sorts of things in the Linux kernel complain about the delay. But either be fast or just hit the breakpoint and look around. So you found a bug. What do you do now? Well, if you fixed it and sent me a patch, that'd be great. Of course, fixing it can be a little bit of an issue because with RCU, Heisenbugs are the common case. And you'd like to debug them. And that can be hard, but here's a few tricks. The overall approach is to make risky operations happen more frequently. In my testing, CPU hot plug is often what's causing the problem or related to the problem, and that's because it doesn't really get tested that much. So I end up doing some of the testing early on for it. And you can give a boot parameter to tell the scripts to do the hot plug more quickly. By default, you'll get a CPU hot plug operation every few seconds. With this boot args in red there, it's going to wait only 200 milliseconds between hot plug operations. So you'll be getting the hot plug operations about an order of magnitude more quickly, and thus putting a lot more stress on whatever might be causing the problem, if it's related to CPU hot plug. Long-lived readers, rcutorture does this automatically, so you shouldn't have to worry about this, but you can always modify the source code if you do. Sometimes there are bugs that happen when the system goes from really, really busy down to idle or back up, and there's a module parameter to rcutorture called stutter that controls how quickly and how often that happens. Some other bugs happen when you have huge numbers of callbacks, and there's a FWD underbar progress module parameter that controls the intensity and how frequently those happen. Another thing that can make things happen more quickly is preemption. And the neat thing is that if you're running on a hypervisor, which these scripts are, you can preempt the guest OS even if the guest OS thinks it has interrupts disabled. Okay, and there's a -- jitter argument to kvm.sh to make that happen. By default, it just makes a jitter script for every CPU that it's using. And each of these things goes and randomly grabs a CPU, spins on it for a while, and lets go, and waits for a little bit, and then randomly grabs another CPU. You can control how long it sleeps and how long it spins, and you can also control the number. You can make more or fewer of them. So these can help accelerate. There's some other things you can do as well, but that'll do for right now. Another thing that it does, we could try torturing RCU from user space. We could have a user space thing, a big test script that went and hammered various system calls and IOCTLs and whatever else to try to make the kernel do RCU work and try to force things to happen. But there's a lot of overhead involved in all that, and so you're not going to be putting a whole lot of stress on RCU when you do that. So we don't do that. What we do instead is these tests are kernel modules. And that allows us to directly invoke the RCU APIs, and thus allows us to put a lot more stress on RCU. All right, so, I torture RCU a lot. Is it really worthwhile torturing it more? A legitimate question to ask, I suppose. Unfortunately, the answer is yeah, there's a lot of reason to torture it more. Turns out RCU, as of 5.15, as in before just the beginning of this week, contains a little over 18,000 lines of code, and that's just WC-L lines. There's a lot of statistics on bug density, and you usually get somewhere between 1 and 3 bugs per 1,000 lines of code. If you work the math, that's somewhere between 18 and 55 bugs. I'd like to think I'm better than that, but I know better. I've been around for a while, and I've seen what kind of code I generate. Plus, the median age of a line of code in RCU is less than 4 years. Okay. In contrast, RCU was introduced in the kernel almost 20 years ago. All right. So there's a lot of new code in there, and new code tends to be buggier than old code. So yeah, there's more bugs in here, and they need to be tortured so we can find them. Sad but true. Another thing working against this is the installed base, and I'm going to illustrate this by kind of running quickly through my career. My very first professional program was written in 1975 pro bono for the National Honor Society. It was, I kid you not, a computer dating program. They used it as a fundraiser. Well, if we had a million-year bug in that program, sequential year program, million-year bug, but whatever, that bug would happen once every million years. So, yeah, Murphy's actually kind of a nice guy, sure. Everything that can happen will. Eventually, maybe in geologic time. As I've moved through my career, I've had the good fortune and privilege to have increasing numbers of people use my software. In 2017, a gentleman from ARM told me that there were at least 20 billion, that's billion with a B, 10 to the 9th power, 20 times 10 to the 9th power, Linux instances running on ARM at that time, about 4 years ago. And that's a lot of systems. If we have a million-year bug, it's happening several times per hour across the installed base. So, infrequent bug, I'm sorry, it's still happening frequently. And it could get a lot worse. We got this thing called Internet of Things. There was, in fact, an LCA about it a little while ago of Internet of Things LCA. And we could easily end up with trillions, even if Linux doesn't get that much of a share of the IoT devices. And my concern is that over a period of 45 years, Murphy might have transitioned from a nice guy to a homicidal maniac. And I don't know about you guys, but I'd feel really, really bad if my software happened to kill somebody. So, this is even worse. So what can we do here? I mean, my current employer is quite generous with systems. I really thank them for providing a good environment for me to test and develop RCU. It's wonderful. But they don't provide me with 20 billion of them, let alone a trillion of them. Nor do I ever expect them to. So what can we do about this? Well, one reason for hope is that there are living things like ourselves. And this evolutionary process has generated us over a period of a fair amount of time, and we are subject to all sorts of ills. Witness the fact that I'm presenting to you virtually rather than being in Australia with you, okay? I'd rather be there, but if I can't, this is at least second best. So yes, there are some problems with living things, but still, we seem to operate fairly well. We certainly live longer than software does generally. So maybe we can use natural selection. And of course, if we're going to discuss natural selection, we need a picture of the great man there, Charles Darwin, who observed natural selection happening in living things. What Charles Darwin didn't know was he was watching natural selection in software of a sort, because we have this DNA, and the DNA encodes proteins and things like that, and it resembles software of a sort. Well, if we can do natural selection on living software, we should be able to do that on non-living software as well. And, that shouldn't be too hard to do. And so let's give the great man something to look at. And here we've got a process for doing this. Now, some of you may object to my bit about software being randomly generated. And I'm sorry, but if you want me to change my description of software in general in the world today, change the software, okay? But that's okay. If it's randomly generated, we can still do validation on it. Run it through tests, formal verification where that's applicable, whatever else we can do, and this will act as a selection function. So we'll get bugs out of that. We'll fix those bugs, hopefully injecting fewer bugs than we fix along the process. And if we do that, we can go around this cycle, around and around, and eventually we have robust software dropping out the bottom. Wonderful stuff, right? Well, almost. You see, we're assuming here that natural selection applies to software, with good reason. After all, living things have this DNA-based software, right? And there's a particularly annoying form of software that is called a bug. All right? So if we go through this cycle, we're not going to have robust software dropping out the bottom unless we're luckier than anyone deserves to be. Instead, we're going to have software and bugs that have adapted to the validation. This, by the way, is one reason that test suites tend to become less effective over time, because the bugs adapt to the test suite and it doesn't find them anymore. What this means is that we have to do more, okay? So one additional thing would be to put a loop on the bottom. As we get bug reports from the field, escapes, yeah, we fix the bug in the software, sure, but let's also fix the validation where feasible so that we'll catch similar bugs in the future. And if we do this, we should have some reasonable chance of getting better software at the bottom on fewer adapted bugs. Still, you have to be a little bit careful. You see, normally what you do is you write, if you write tests at all, hopefully you do, okay, you do write tests, right? When you do that, you're going to validate the use cases you're aware of. I mean, write a test case for a use case I'm not aware of, what would I write? And then what happens is we randomly generate our software, which has lots of bugs. We run the tests and fix the bugs, and if things work perfectly, we get rid of all the bugs that the test finds. And then we do it again, right? And then we end up something like that. Okay, well, our users aren't inconvenienced by the bug, so what's the problem? Well, the problem is, of course, that the world changes. And so we're likely to get some new use cases. And what we'll find, if we've been doing this, is those new use cases will have been protected from our software by walls of bugs. And the poor guys that are trying to make those use cases happen might quite understandably decide, this is a real pain. I'm going to write my own software. Thank you. This isn't working. Now, don't get me wrong. Life is sometimes hard, and sometimes hard choices have to be made. And if you're in a situation where you can only fix one of two bugs, yeah, you're going to fix the one that's hurting your users right now. But understand this is where that leads to. So what we'd like to do then, if we have the luxury of doing that, and sometimes we do, instead of just bug reports, we'd like to add paranoia and make the validation a little bit more aggressive and try to clear the way for future use cases. And the fuzzers actually seem to do a reasonable job of that, at least so far. So we are already doing this to some extent, and hopefully that'll continue. Okay. Another thing is that natural selection is a euphemism for a rather ugly process, actually. But sticking just to software and avoiding living things for the rest of the slide, the key point is, if your tests are not failing, they are not helping to improve your software. That actually bears repeating. If your tests are not failing, at least from time to time, they are not helping to improve your software. They might be maybe preventing bugs from coming in, but they aren't actually improving it as it is. So, what's the price then of robust concurrent software? As you know, internal bug fixing, we all know that, we've done it, but also eternal validation development. Especially in the popular things like the Linux kernel and any number of other popular software projects, new use cases appear all the time, and we need to prepare the software for them. So we've gone through these topics: torturing RCU, tracking down Heisenbugs, installed base causing trouble, natural selection, good and bad and ugly, and the price of concurrent software. This next slide is where you can find some more information, as is the slide after that. And with that, if you've got questions, I'm happy to answer them or at least say something in response to them. So any questions? Hearing none, thank you all very much for your time and attention. Here we are. Oh, we do have one. Okay, I guess I spoke too soon. Okay, should we view the rcutorture as a pass-fail only, or are there statistics that can flag performance regressions? That's actually a good question, and that gives me an excuse to revisit an early slide. Let's get back up to it. Eventually here. Yeah, there we go. Okay, that slide. There are some statistics. The column after all the dashes is the grace periods that were executed for the full test, and then there's also per seconds. As you can see, the different types of RCU have rather wildly different statistics on the number of grace periods per second, and that's life. They're doing very different things. The type of RCU being tested, so tasks root is one that uses work queues to interrupt all the CPUs, kind of the old style approach, and so on. And so it'll give some state information pertaining to that type of RCU there. The grace period number and the flags thing that says whether there's a grace period being asked for. There are a few types of RCU that are robust enough to be able to stand having piles of callbacks jammed down their throats. And for those, and if you've selected the test, that's the progress kernel parameter we talked about earlier. It'll tell you the maximum queue depth of callbacks. And so the tiny ones, which are single CPU, keep up fairly well. The worst case is tree 03, which it makes things hard on its configuration, makes things hard on RCU, And there was a point in time when there were, in this particular run, 10 million callbacks, 1 million callbacks waiting to be invoked. So there's some statistics. Let's see, I've gotten behind on questions. The statistics, some of the statistics are really noisy. For example, the Nmax CBs is quite noisy, and so you have to be a little bit careful of relying too much on that one. What's failure look like? You're right. I should have a slide on that, and I don't. What'll happen is between these, you'll see these lines, and then if there was a failure after the line corresponding to the test that failed, there'd be stuff printed out which could vary really wildly depending on exactly what failed. It'll give a summary of I got this many warnings, I got this many stalls. It'll print out an occasional thing about what's going on. There's quite a bit of variety on the failure reports. Can more testing be done with emulated timing to hit interest case and concurrency bugs rather than relying on large numbers of machines and doing things randomly? There is a little bit of that in RCU as it is now. There are places in the grace period K-thread where some of the tests will insert delays. And if I remember correctly, that's one of the reasons 303 has a hard time. What'll happen is that it'll randomly insert delays as you ask it to. In addition, there's random delays inserted in the readers that are being done. You could, of course, do that quite a bit more. There have been, at ETH Zurich, I believe it was, about 10 years ago, there was a project that would insert those automatically based on various things. Perhaps another sanitizer sometime in the kernel's future will do that automatically throughout the kernel. How can we identify which torture is the most relevant to an employer's use cases? Okay, let's take a look at that. One thing to do is to look at the kernel you build and see what RCU-related kconfig options it uses. And so one thing you could do, there's a directory. What you can do, in fact, to find that directory is just, for example, do a find .-name root01-print. Okay, and that'll show you the directory where the root01 file exists, and that root01 file defines the kconfig options for the root01 scenario. There also is a root01.boot file. The boot file is optional, and if it exists, it'll have boot arguments that help define that. So what you could do is just make your own scenario for your employer. Just go and drop the file into that directory. It's tools, testing, self-test, rcutorture, configs, RCU, and then the names of the files. And so you can put my company, it has to be all caps. You can have dashes, but it has to be all caps. This is an old thing, so that's why there's lowercase t and u there. And put in the kconfig parameters that match the kernel you guys use and get exactly what you want. And then also the boot .boot file if you have boot arguments that you care about. And then you can run whatever you want. Otherwise, what you can do is just go through the existing files and see if there's one that's a close match, and there might well be. There is another file in that bin directory called config.csv.sh, and that'll make a spreadsheet of the existing ones, the ones that are run by default. And you can look at that and get a quicker view. How often are you finding this is catching bugs in new patches? If I write a patch, I probably have an rcutorture failure in my future. I sometimes find problems in other parts of the kernel. There was a rcutorture failure that showed up just before Thanksgiving, and I forget where it was. Frederick Weisberg took pity on me and chased it down for me, so I could celebrate USA Thanksgiving holiday. He's in France, so he didn't have that one. I hope to return the favor someday. We found some things in the scheduler. We occasionally find things in timers. And so, but mostly, I'll write a patch, I'll run rcutorture, and it'll explode. Anyway, I think we're at the end of the session. Thank you all very much for your time and attention and for all the good questions. And have a great rest of the conference.